Hello, this is Mrs. Davis. I'm going over AP Pre-Calculus Lesson 1.5, Polynomial Functions and Complex Zeros. And we're going to start with a review just of imaginary numbers. So we start out talking about the principal square root of any non-negative real number. So if you just have the square root of 9, that's 3. And that's called a principal square root, when you don't have to worry about a sign in front or after, and it's just telling you, hey, take the square root of 9. Okay, when the value of the radicand is negative, it's said to be an imaginary number. So if you had the square root of -9, that's an imaginary number. Now, what you have to know about imaginary number is that it's an I, and it's defined as the square root of -1. So if you look at this example, they take the square root of 9, and then they split it up, the square root of 9 times the square root of -1. So basically they've split it into two square roots and created a -1 square root. So then they take the square root of 9, which is 3, and then the square root of -1 is I. So that's the rule. All right. And also, you just write it like 3I. The I comes after. So that's how you get an I from a negative square root. So let's just do -25, square root of -25. All right, you don't have to do the steps here. You can just go, okay, that is 5I. Okay, so you would take the negative out and put an I, and then it's just a square root of 25. Okay, so now we start to talk about complex numbers when we add imaginary numbers. So a complex number is a number of the form A plus BI, where A is the real part of the complex number and B is the imaginary part of the complex number. And that's why we try to always write it the same way, a something plus something I. Okay, so the fundamental theorem of calculus is something else we're going to talk about. I mean, of algebra, not calculus. And it just guarantees that any polynomial function x with real numbers coefficients can be factored completely over the set of complex numbers. So if you've only been thinking about, oh, well, if I get an x squared plus 25, I can't factor that. And actually you can under the imaginary numbers. And so they walk through how you can do this in these notes, where you can just figure out what it is with i's. And they also say that in this fundamental theorem of algebra, that you will have the same number of zeros as you have the degree, and they might be complex. You know, they're all complex, I guess, because you can have no imaginary part. But they'll either be real or imaginary. All right, now reals come in pairs. I mean, sorry, I keep messing up. Imaginaries come in pairs. And so if you have a third degree and you have two imaginary, that means you have one real. So you can kind of figure some things out. So every complex function of degree greater than 1 has exactly n complex zeros, and some of those zeros may be repeated, meaning that would be multiplicity. So I think the best way is to just start working through some of these. So the first example says, hey, factor this completely using complex numbers. And it wants us to factor it, not solve it. So the first thing we're going to do is factor out an x. We see each term has an x, so we get x squared minus 6x plus 13. All right, and okay. Now, how I would factor this part is it's not going to factor evenly using real numbers. because nothing multiplies by 13 and then adds to -6. So I'm going to complete the square, so this is good practice. So I'm going to say this is x, and then I'm going to come over here and I'm going to complete the square with this. And so I'm going to say x squared minus 6x plus something equals -13 plus something. Okay, and so this is going to be half of 6, which is 3. 3 squared is 9, so I'm going to add 9. So this factors to x minus 3 quantity squared. And then you have over here -4. So far I have a factor of x, and I have I'm not done here. I have to say what this becomes. So when I take the square root of both sides, you see I have that imaginary part there. So I get x minus 3 equals plus or minus the square root of -4. And the square root of -4 is I, and then the square root part is 4, so that would be 2i. So this part becomes 2i. So you get x minus 3 equals plus or minus 2i. So you get x equals 3 plus or minus 2i. Now I have to write that in factored form. So I would get x, and then I would have x minus 3 plus 2i, and x minus 3 minus 2i. And if you want to simplify that, that can come to x minus 3 minus I, and x minus 2i, sorry, plus 2i. Okay, so there's factored completely, and it uses complex numbers. Let's look at another example. This time we have two variables, and so we can factor out a y first. So we get y, and then we have 4x squared plus 25. So now we want to be able to figure out what 4x squared plus 25 is. So we would say, set that equal to 0. So 4x squared is -25. So x squared is -25 over 4. So we have x, taking the square root of both sides, x equals plus or minus the square root of -25 fourths. And so if I take the square root of that, first let's take the negative out. So I have x equals plus or minus I. And then the square root of 25 over 4 would be 5/2. And you rewrite that, x equals plus or minus 5/2 I. So now let's write it in factored form. I would have y, and then x minus 5/2 I, and x plus 5/2 I. Now you could rewrite this as 2x minus 5i, but it's okay to keep it as a fraction. All right, so let's just do this one last thing on this page. The conjugate root theory says that if f of x is a polynomial with rational coefficients, then the irrational roots of p equals 0 occur in conjugate pairs. So if you have a plus the square root of b, that's a root, then so must a minus the square root of b. That's its conjugate. They have to come in pairs. So if you have an a plus square root of b, you have to have an a minus the square root of b. And also, if you have a complex number, a plus bi, and that's a 0, then it also means a minus bi is a 0. And that draws to a corollary that says a polynomial function of odd degree with real coefficient has at least one real zero. And that's because these things appear in twos. So if I have a 3 degree, I can have 2 irrational and 1 real, or I can have 2 complex because these things come in pairs, and 1 real, or I can have 3 real. So that's why it says it has at least 1 real zero. It's not going to have 2. There's no way an odd function could have 2 real. And so what we do is if it's degree 3, we could say it has 3 or 1 real number, real root. And if it's 5, we would say it has 5 or 3 or 1 because the other ones come in pairs. All right, so I'll stop that video here.